All right, guys, in this podcast, we're going to talk about balancing chemical equations. All right, basically, let's first define what a chemical reaction actually is. Chemical reaction is when you change the substances that you start with into one or more new substances. So the atoms are rearranged into different combinations to form something different. All right, how do we know that a chemical reaction has occurred? Well, just like in that lab, we look for signs that a chemical reaction can occur. These would be change in energy, so sound, heat, light, formation of a gas, formation of a precipitant, which is a precipitant is a solid that is formed in solution during a reaction, or a change in color. Okay, now the only way to actually confirm a chemical reaction would be at the microscopic level where we could actually see that the atoms have rearranged. But in the absence of that, these things are the next best indicator that a chemical reaction has occurred. All right, now we write chemical reactions in what we call chemical equations. In this equation, you see you have A plus B yields, that's what this sign means, C plus D. The first side is called the reactant, so the things that we start with and we mix together, those are the reactants. And then what they produce, what they make, is called the product. So the left side of the equation is always called the reactant, and the right side is always called the product. All right, there are steps to balancing an equation. We're going to go through some of them real quick, just to give you an idea of what we're talking about. First thing you want to have is you want to have an actual unbalanced equation to look at. You want to have an equation that you can visually look up and see. You don't have to think back or refer back to something else. Second thing you want to do is you want to be able to count the atoms on each side. You're going to count all the carbon atoms on each side. You're going to count all the hydrogens, whatever you have. Then you're going to add coefficients, which are big numbers in front, to make the number of atoms on each side equal. And remember that a coefficient times a subscript is going to tell us our number of atoms. Then we can reduce our coefficients if it's necessary to the lowest possible ratio. So we're going to look, make sure they're in the lowest possible ratio. If not, we'll reduce them. And then we want to double check, make sure everything went like we had planned. Okay, so we're going to look at this first example. All right, so first thing you want to do is you know that this side, you're adding aluminum and nitrogen together. Okay, so these are the reactants. That's what the equation is starting with. And then over here is the product. So you want to kind of think of this little arrow like an equal sign. It kind of divides your equation. So I'm going to use this as my dividing line, and I'm going to write the elements that I have, aluminum and nitrogen, and I'm going to count them. So on this side, aluminum, I have 1. And nitrogen, I have 2. On this side, I have 1 aluminum and 1 nitrogen. Okay, so I want to add coefficients, big numbers in front, to try to get the nitrogens and aluminums equaled out. Aluminum is good right now, but we've got to look at the nitrogen. We need 2 nitrogen on this side, so you put a big 2 in front, so you got 2 nitrogen and 2 aluminum now. Okay? Now, when you're looking at this, now your aluminum is messed up. Now you have 2 aluminum over here and only 1 aluminum over here. So I have to put a 2 right here. Gives you 2 aluminum. All right, now you're all balanced out. So you got equal numbers of aluminum and equal numbers of nitrogen. Okay? Now what goes in this little hole? Well, you can put nothing there, or you can just write a little imaginary 1 there. Okay, that's presumed to be a 1. All right, let's look at another example. All right, here we go again. All right, we got aluminum and oxygen. Okay, so we're going to write down our aluminums and our oxygens. All right, we got 1 aluminum on this side, 2 oxygens, and on this side we've got 2 aluminum and 3 oxygens. Okay, all right, now let's try to balance this out. We could start with aluminum if we wanted. We need 2 aluminums here. Okay, now with the oxygen. What can you multiply either of these by to get to a common number? Well, in this case, the common number would be 6. So we want to get them to 6. We'd multiply this side by 3. 3 times 2 is 6. And on this side, we want to multiply by 2. Now, 2 times 3 for the oxygen is 6. But it also changes the aluminum. Now we have 2 times 2 is 4. So now oxygen's good. We've got to go back and fix this aluminum. So instead of a 2 here, we really needed a 4. Okay, so now you have 4 aluminum there. Okay, let's look at another example. All right, here we have phosphorus and oxygen. Got 1 phosphorus, 2 oxygen. And on this side, we have 2 phosphorus and 5 oxygen. All right, P, let's see, we need 2 P's. This little 2 there gives us 2, so our P's are good. Now oxygens, you got 2 and 5. Okay, well the only number that will get them to the correct number would be to get them both to 10. So this one by 5. 5 times 2 is 10. And now this one by 2. 2 times 5 for the oxygens is 10. Now the P. 2 times 2 is 4. I have to go back over here and we have to change that P there to 4. Alright, let's look at another example. Alright, now we're getting a little more complicated here. Alright, we got K, Cl, and O. Okay, on this side we have 1 K, 1 Cl, 3 O's. On this side we have 1 K, 1 Cl, 2 O's. So the O's are obviously the problem. We need to get them to 6. Alright, but this one over here also changed the K's and the Cl's to both 2. Now you need a 2 there. Okay? Ooh, stepping it on up. Alright, in this one, you can do one of 2 things. You could break all this up, or you can recognize that you have polyatomic. NO3 is a polyatomic. CrO4 is a polyatomic. If these same polyatomic ions appear on the other side of the equation, you got CrO4 here, so that's good, and then you got NO3 here, that's good, then you can just count it as a unit. So when we're writing our atoms here, we can count NO3 as 1 unit all by itself because it's a polyatomic. The same for CrO4. Okay, we got 1 Pb, 2 NO3s, 2 Ks. Now CrO4. You might want to say we have 4 of them, but we do not. Remember, CrO4 is like this. So really you just have 1. Okay, over here you have 1 Pb. Again, you don't have 4 CrOs, you have 1 CrO4. Alright, and you got 1 K and 1 NO3. Okay, again. Alright, now you have 2 NO3s and 2 Ks on this side. So put 2 right there. That'll take care of all your problems. See, that one was actually relatively simple. It looks scary though. Alright, here's a different kind of issue. On this one, we have OH, which is a polyatomic, but on this side, it's not OH anymore. Now it's broken up. Okay? So you have to approach this one a little differently. So let's count first. We have 1 Fe, 3 O's, 3 H's. This side we have 2 Fe's, 2 H's. Now let's talk about these O's. See how the O's are in 2 different terms over here? So you got 3 there and 1 there. 3 plus 1 is 4. You have 4 O's. Anytime there's a split like that on one side, you want to save that element's balance last. Hope it just works out for you. Okay? All right, so let's look at the Fe's. Okay, so we need 2 Fe's. We're going to put 2 right here. That's going to change everything, right? Now we're going to have 2 Fe's on that side. And 2 times 3, 6 O's. And then 2 times 3 again, 6 H's. Okay, so now we got to go over here. Our F's are good. O is not right, but he is never weird, so we're going to save him for last. And then we've got our H's. We need 6, and we only have 2. So we're going to have to multiply by 3. So now we have 3 times 2, 6 H's. Now let's look at these O's. We have 3 O's right there, and then 3 O's there. 3 plus 3 is 6. Okay, and see, it just works out for you. So if you save those for last, 9 times out of 10, it'll work out for you. All right, here's some other helpful hints since we just went through a couple practice problems. Always balance one element at a time. Never try to do 2 or 3 at one time. You'll get so confused. Make sure you update the atom count, meaning once you add a coefficient at the top, make sure you go back down below and correct it. If not, you won't get the right answer because you won't be keeping up with yourself. If an element appears more than once, just like on that last one we just did there where we had the O's that were split, we're going to balance it last. And then if you have a polyatomic ion and you see it on both sides of the equation, go ahead and just balance it all together as a unit. All right, let's look at one last problem. All right, this is CHO, what we got here. We got 3 C's, 6 H's, and 2 O's on that first side. And then 1 C, 2 H's, and then we got split O's. We got 2 and 1 gives us 3 O's. Okay? All right, let's start with the C's. So we got 3 C's. We're going to put a 3 right here. Okay? Then we got to update our O's. We got 3 times 2 is 6 plus 1 is 7. Okay? All right, now our H's. We got 6 on this side. Let's put a 3 right here. 3 times 2 is 6. Now we got 3 O's right there. And then 3 times 2 is 6 right there. 6 plus 3 is 9. Okay? Now, here's where it gets a little funky, right? What times 2 gives us 9? 4 1/2. Okay? Here's the issue. You can't have half of an O2 molecule. It just doesn't work. Well, to get rid of a half, you multiply everything by 2. We're going to multiply all the coefficients in this problem by 2. So there's a 1 here. So that'll be 2. 4.5 times 2 is 9. 3 times 2 is 6. And 3 times 2 again is 6. Now we're going to go back and make sure it all worked out. So on carbon, we got 2 times 3. Sorry, son came asking me a question. All right, here we got carbon. 2 times 3 is 6. Hydrogen, 2 times 6 is 12. Oxygen, 9 times 2 is 18. Okay, this side we got 6 carbons. Then we got 6 times 2, 12. All right, then we got 6 times 2, 12 hydrogens. And then that's 6 oxygen. 6 plus 12 is 18. Okay, so it all works out. Okay, so anytime you approach one and you have one where it's uneven, go back and multiply everything by 2. It'll get rid of that 0.5. It'll all work out.